We have another graduate student that volunteered to be our TA. His name is Devi, and Devi will be your grader. However, for this particular exam, because this is what Andrew did grade, if you have any problem with it, talk to me. Don't talk to Devi, and don't talk to Andrew. So I'm going to go through the solution right now. And if anything does not make sense in your grading, just send me the email. Don't email Andrew. He's not our TA anymore. He's going to be working in full time in his research. And Devi didn't grade the exam, so it's not really his responsibility to actually talk about it. Okay? Good. So the first problem. So the grading of the first problem is a little bit tricky because there is no numbers in it. You know, regular problem would be, here is the equation, here's my numbers, and here's my solution. So I discussed with Andrew how he graded this, and so we basically figured there are 4 things that he's asking you to do. He's asking you to show where is V, W, and U at the inlet of the rotor at the top position, because that rotor, the rotor is the moving part, the stator is the fixed part. So you can plot the velocity diagram or triangle here, or here, or here, or here. He wanted you to plot it at the top center, at the top position. So you're supposed to plot the velocity triangle over here, at the inlet of the rotor, not the exit, the inlet of the rotor. Okay, so 1, 2, 3. And then he asked this question, is this an impulse or reaction turbine? Okay, so since there are 4 of them, I told Andrew each one of those will be 1 point. And if people try to attempt the problem, even if they did it completely wrong, they still get 1. So if you try to attempt the problem, you should at least get 1. And if you get those 4 things correct, you should get the extra 4, you get 5. You do any one of them wrong and you should lose a point. So now, what is the correct solution for the velocity triangle? How it should look like? So this is a stator, right? The fixed part outside of the stator. Notice how small this turbine is. This turbine actually was made at MIT. When I was a graduate student back in 1997, you know, a professor came to us in Michigan from MIT and he was showing us those new turbines, and like there was like very hype about it. Everyone was so excited that we can make turbine that small. That basically means that every one of us, rather than having a battery in our cell phone or something, will have a small turbine, and we just give it a drop of oil like gas, and that turbine will spin, you know, and get electricity forever, basically, rather than battery. But small as it is, you know, it has problem too with something making turbine that small. A lot of things come when things are really that tiny. Anyway, it's really a turbine with a stator and a rotor. So the stator, what's the job of the stator in a turbine? I would say also spin the flow for the rotor to be spun by that spinning flow, right? And they do this on the expense of pressure. The stator eat pressure and generate velocity. Velocity with big V theta. So here is, if I zoom in, this is the inlet, huh? Not this, because the flow would be coming like this. So this would be the actual inlet, and this would be the actual exit. So this guy will be shooting like this. In what direction? Direction of the plate. Huh? You are holding the hose and you are watering your yard. The water cannot go this way. The water has to go with the hose in the exit. So the velocity leaving the stator is the velocity entering the rotor. So this, especially on the top center, this would be the direction of V1. So I'm gonna call it like this. So now, you know, is it like really this or like this? I told Andrew, you know, don't be so picky about which way, you know, but it's not this. If you should V this way, totally wrong. But you know, because it's a sketch, this is okay. This is okay. You know, this is okay. But this is not okay. I mean, it cannot be shot horizontally, otherwise it will not really go into the rotor. So I just need it to be with an angle that look, you know, tangent to this. Okay. So now V, I just plotted V with this triangle. Now where is U? U should be in the, U is the tangent velocity. Sorry, it's the plate velocity, right? And that velocity is omega r. And if I want to see which direction it will be over here, it will be tangent to that circle, right? Omega r. Now the question is it going to be to the right or to the left? Should plot those with an arrow, actually. So is U going to be from right to left or left to right? Left to right. Anyone else? Okay, so like going this way or this way? This way. Yes, why? Why do you think it's going this way? That is the correct answer. Why it should go from here to here? Why would this turbine spin in this direction? Clockwise. What's your proof? Yeah, because it's spinning because of the V. If we are shooting V in that direction, why would it go the other way? If I am kicking you in front of me, why would you come to me? I mean, you have to run away from me. If I keep punching you, you should go away from me. So if the velocity is pushing it this way, it needs to rotate this way. So that is U. Okay? So if V is like this and U is like this, W must be up or down? It's going to be down. Why? That's correct. Why? W has to be down. Yes, because the equation U plus W equal V. So knowing that U has to be like this and knowing that V has to be like this, W has to come like this from the velocity triangle. And also from what is the other proof that W has to go like this? The direction of the rotor. The rotor expects velocity to come this way. The velocity cannot go to the rotor this way. You cannot enter like this. If this classroom like this door is like well-designed door, you know, people should approach it normally, not like with an angle. They should allow the passage to really guide toward it. So W has to be going like this. So I find this really very amazing how like the absolute velocity is going this way, but the rotor actually will see it this way. And how is that possible? Like the flow is actually going to this is my left, going from the left, but the rotor will see it going from the right. The reason is U is so huge in those turbines. So when those turbines, they first make them, they spin with a huge RPM. 100,000 or something. It's like, it's amazing how quickly the speed is on those small, tiny things. Okay. So that's basically, now the question, is it reaction or impulse? What's the difference? An impulse turbine does not have drop over the rotor. The rotor is just for flow direction, but does not change the pressure. So how does it look like? If we Google an impulse turbine, we will see that it looks like a cup, kind of like the built-in wheel. Impulse turbine plate, rotor. You wish you see an actual thing, not just a sketch. So like this, he's saying this is an impulse turbine. So the inlet area and the exit area is the same. The flow just go and turn. But in something like this is actually, the area is different in the inlet and exit. There is pressure drop in the exits and inlet. So maybe, so usually in a steam turbine, the first stage is impulse turbine, impulse steam turbine. So I mean something like this. I cannot see the picture. So my point is that it's like this. It's just like a cup. Just like inverted U. Go up and then invert and go down. So you change direction. So impulse or reaction turbine, This one. This is impulse, because look at the rotor. It's exactly symmetric. When it's not symmetric, like this is not symmetric. It's not a U, it's like an airfoil. And although it does not really show that well over here, but because the plate a little bit bigger, but if you look at the actual inlet area and the exit area is smaller. So basically the rotor looked like diffuse, like the stator, where the stator job was, let's speed up the flow, let's drop the pressure and make the velocity go faster by doing what? By having big inlet area and small exit area. The rotor do the same thing, but the other direction. So when the rotor drop the pressure, it is a reaction turbine. When the rotor does not drop the pressure, but just change direction, that's an impulse turbine. The pressure drop ratio between the stator and the rotor, is it 50-50 or 70%, 30%? That's what they call the degree of reaction. Okay? So I told you, I guess, one time we were visiting Jinx power plant, and the technician was making fun of the student and saying, well, this is an impulse turbine, but you guys probably don't know this. And one of the students said, no, we actually know. We studied the difference between impulse and reaction turbine. And I was so proud. I was like, he couldn't really make fun of my students. So impulse or reaction turbine? It's a reaction, but you know, when I look at the shape of the plate, it's not that much. It's not tilted that much, right? But I mean, if we look really a little bit careful, maybe we'll see that this inlet area is a little bit bigger than this because of the way the plate is built. Okay. Look at this one. Ouch. So I guess by changing the angle, you can change the speed up of the flow inside the rotor. All right, so back to this is very clear whether it's impulse or reaction, right? What do you think that rotor is doing? Here is the inlet area, and here is the exit area. Impulse or reaction? Reaction, of course, right? Because the flow will really speed up as he's going through that rotor. All right? Good. Does this turbine work? Can this turbine work as a compressor? If we turn it the other way, so rather than spinning it this way, what if we spin it this way? What will happen? The flow will come here. Again, the actual flow, the absolute velocity at the inlet of the rotor now, this is the rotor. And if we turn it into a compressor, turn it this way, this would be the inlet, right? So V1 would be coming like this. Does V1 come with a twist? Does it come with V1 theta, or does it come all radial? Imagine a compressor, and this rotor will be connected to a pipe, and so a duct, and the air will be rushing into that rotor. It will come all radial because there is no reason for the flow to come with a twist. We are sucking him. He will just come, surrendering himself to us. I'm here. You made vacuum. I'm coming from the atmosphere behind me, and I'm rushing toward the vacuum that you guys created here. And why the vacuum is created here? Because as this guy spin and kick those guys out by centrifugal force, they create a vacuum behind them. So the flow, although V absolute would be like this is going to be an excellent problem for the final. I could tell you in the final, this turbine can also run as a compressor. Please plot for me the velocity triangle at the inlet and the exit of the rotor, for example. So you're going to make V1 like this, and U need to figure out that U by yourself. Should you turn counterclockwise or clockwise? And why? Your gut feeling should tell you, well, because it's a compressor, and now we know the turbine was going this way, the compressor has to go the other way. But also, what's the other reason? So it's going to run counterclockwise, but what's the other reason why it should be running counterclockwise? The stator is a good reason too. So Denver is probably thinking that if I turn it this way, the flow at the exit of that rotor will be going which way? Will be going this way. And that stator will be perfect for him. Right? But the other reason is also this. Look at the inlet of the rotor. That rotor is expecting W to be which way? This way. Right? I mean, that rotor, if W go this way to that rotor, that would be a disaster. That rotor expecting W to go this way. So for W to go this way with a V that's this way, V vertical, and W coming this way, U must be like this. So U plus W equal V. So U has to be this way. So therefore, this guy has to go this way. All right? Make sense? So maybe I should. Yeah. Let me draw this first. So what I was saying, that V is going this way. This is V, right? And W has to be this way. I'm sorry, U. So this way, W would be like this. And you get the equation, U plus W equal V. And so that velocity triangle, that velocity is perfect for this. This is a good direction for W to get in. And now once you go into that stator, once you go to that rotor, one should expect V to actually go a little bit this way, right? Because of the twist. And there is bigger U, right? On the top, because of the difference in the radius. So W need to be a little bit more bent this way. So that's why the blade is going that way, right? So that twist in W will make V, still V will have to go this way. Understand why V has to go this way? Because we are the one spinning it. It's a compressor. And so now that V will go into this stator now. The stator is going to be a diffuser for them. They come at a small area and they leave a bigger area. And what's the results of going through this diffuser? Reduction in velocity and increase in pressure. That's the point of a stator of a compressor. The stator of a nozzle come first and he reduce the pressure and increase the velocity. The stator of a compressor come next after the rotor, and his point is to reduce the velocity and increase the pressure. And in both scenarios, the rotor itself doesn't do anything except for, let's give V theta, or let's extract V theta. That is the currency in the rotor. And the stator, and sometimes the rotor deal with pressure too. Right? In the action rotor, they also increase the pressure by the passage, or decrease the pressure by the passage. Okay, Denver, you had a question. Okay.
I was thinking about the blades, the way they're shaped, but shouldn't it be the other way around? But then again, if you did that, then it would be forming that low pressure on the back side of it as it's spinning, right? So it makes sense to have it the thicker side on the outside.
I'm not really hearing your question, Will, but I bet you are wondering why the rotor plate, in case of a compressor, should be tilted this way. Is that what you're asking about? Because the compressor plate doesn't have to be bent. See, if we are rotating in this direction, those plates are called now, the rotor are called bend forward or backward or radial. The rotor plate in this scenario, it's a compressor, and we are turning counterclockwise. Those plates are now called bent backward or forward or radial. They are bent backward. There is actually compressor plate that is, or pump. I mean, this is also the same geometry for centrifugal pump, where they are bent forward, not backward. Okay? And of course, there is which is more common, just the radial kind, right? All of them will always have a V. Don't make any mistake about this. V will always have to be in the direction of rotation. V2 at the exit, you are leaving a rotating compressor or rotating rotor. You have to leave with that twist. The bad example I always give is that the first time I give that example, my kids were so small and I used to take them to the parks all the time. And there is always those big wheels where you put all the kids and all the parents rotate the kids. And so I was under this picture in my head last time I took them, and I said, well, if you have your kids on this rotating thing and you spin them so fast and the kids start zooming up, they've flown away, they will flow in the direction of rotation. It's a horrible example because kids are being hurt by that example, but you can see how when you leave a rotating disk, the kids has to come in the direction of rotation. The same thing for the flow. Whether the plate is bent backward, forward, whether the kid is facing, he's giving his back or forward, they all need to spin out in the direction of rotation. So the stator will always have to be in this direction. Okay, well, what is the difference then between backward and forward tilted rotor? The difference would be in the velocity diagram, huh? So W would be like this, and U would be like this. That's V. That's for bend forward. And if he is radial, you will go like this, and this would be your U, and this would be your V. Okay, and if you are backward, bend backward like this example, you'd go like this, and V would be like this. In every case, W plus U, W plus U, W plus U. But surprisingly, that velocity triangle affect what really matter at the end, because we don't build those things to spin the flow. We build them for the HQ curve, right? Or the delta BQ for a compressor. So amazing, that curve would flatten up, or even will have a little bit of a hump like this, depending on are you radial or bent backward or forward. So the characteristic of the HQ curve depend on the geometry of the rotor. And some would be advantageous than others. Okay? So what's important here is, remember that U plus W equal V. And remember that the plate geometry determine the velocity leaving, right? And remember that those turbo machine have to give V theta if they are a compressor. The rotor give V theta and consume V theta if he is turbo.
Dr. Salam, I have a quick question.
Yes, raise your voice.
Can you please go to question number 1 for problem A?
Yes.
So the angle between that U and W.
The angle between U and W.
Yes. So
Which
does it?
This is U. So U has to be horizontal and W has to be going down like this, right?
No, W.
Sorry. Yeah, W is this one. Sorry. Yes.
Yes.
This is W over here, and this is U. So U direction has to be horizontal. W, I told Andrew that when he grading, W should be aligned with this passage. Why this passage? Because we are doing the top center. So in the top center, the W has to be, for a good design, it has to be like this. Okay? So if you made W vertical or, you know, like I guess he was a little bit more, what's the word? A little bit more conservative when it comes to W, because you should know that W need to go between those two plates. Make sense?
Yes.
Okay. Good.
Thank you.
So U plus W equal V. All right, the second problem. We had this problem in the homework, but they asked for completely different thing. In the homework, you said calculate the maximum power. And in the homework, this is the homework. He has the equation for the torque. He has the equation for the power. What's the difference between the torque and the power? One thing. What is it? No. What's the difference between torque and power? one variable between them. You multiply the torque by something, you get the power. What it is? Omega, right? The radian per second, the rotational speed. So he multiplied this torque time omega, huh? And when he does this, omega with the r over here become the u. Okay, so the only difference between the torque equation and the power equation is that u. It was originally r, but because you multiply omega, it become u. Okay, and so this is the power for any rotational speed, huh? Omega, or basically u. You give him the u or the omega, and you get yourself your power. There is a maximum power. If you spin too fast or spin too slow, that's not the maximum power. The maximum power happen at u equal v1 over 2. And so when he substitute this in this equation, he get power max. Okay, and that's what we use in our homework. Of course, you need the m dot, and the m dot is piece of cake. It's rho AV, right? Rho AV. And V is what? The V jet leaving here, and the area is the diameter of that jet, 1 inch, right? And the rho is rho water. So that m dot, I mean, we can just say this is m dot jet, really, right? This is m dot jet, and because there's 4 of them, he multiplied by 4. That's what we did in the homework. Questions about the homework? We understand the homework. Very good. Now he said here he wants the maximum torque, and he put it in italics. Okay. When maximum torque will happen? When the velocity is 0, right? So this is basically someone asking you, how much torque does it take to arrest this? We want a brake. We need to design a brake to make this Belton wheel stop for emergency. A child gonna hit, or like someone we need to immediately arrest this thing. Okay, until we finish the water or something. So the maximum torque will make the velocity 0. Okay, so this equation is the torque at any velocity. What velocity are we interested in? U equal, this is the equation for the torque at any velocity. What velocity I'm interested in? U equal
0.
0. If you set u equal 0 over here, that's what I'm saying here. If you set u equal 0 over here, you will get 4 times m dot jet, and this would become r minus v1, right? R minus v1, 1 minus cosine beta over 2. Okay, or simply m dot r1 minus v1 plus v1 cosine beta. Okay, so we can just come up with that number immediately just by making u equal 0. I also kept telling you that this chapter is all about one equation, and that equation is torque equal, let me get rid of this drawing thing, doesn't help. The torque is equal m dot, or 4 m dot jet, because there are 4 of them, r2 v theta 2 minus r1 v theta 1. That is the equation of the chapter. R2 v theta 2 minus r1 v theta 1. And when you do this, you look here, and this is 1 and this is 2, you realize that v theta 1 is v1, because v1 is all tangential. So that's why it's minus v1. Okay, and at the exit at 2, well, it's some is radial and some are tangential. So I'm gonna take v2 cosine 135, v2 cosine the beta, right? It should be beta 2. Okay, and so it's r2 v theta 2 minus r1 theta 1, and so it's the same r, so that's why r1 is out, and you see here is the 2 and here's the 1, and you notice that how v1 and v2 is the same. So either way, whether you're gonna start from this, you will immediately realize this is the equation. Okay, or if you have this equation for a built-in wheel and set u equals 0, you will end up also with the same equation. Okay, so the answer is 4 times 1.057 multiplied by minus v1, so minus 100 times 1 minus cosine 135. So it's not 100 square, because that was like what, vjet square. So questions. So now, how does this problem was created? So this problem was created out of 3 scale. Basically, if you said what's given, you get 4 points. If you write the equation right, which would be this one, and the equation for m dot, or you can start from this and set u equals 0, and still you need an equation for m dot. You get 4 points for the equation, and the final answer, which I don't know what is it. How much is it? It's, so this would be
722.
722.
Fit LB, yes.
Okay, 4 times 105, 1057, 1057 time the 100, right? Time 1 minus cosine 135. Right? And it should be negative because it's, I mean, resisting the motion. So you'll get, because it's minus 100. Okay? So that is the answer. Questions? Very good. Third problem. 800 turbine. Each one of them behave like this. Okay? 800 turbine, each one of them at rated power produce 2.5 megawatt, and off, when the speed is lower, you get less and less power according to that curve. Okay, what does he want from us? He said the annual, no, please calculate where? Please, yeah, please calculate the annual megawatt hour. So the megawatt hour, the energy, megawatt hour, or kilowatt hour, or joule, or BTU, all energy is power multiplied by time. You need to multiply the what? Multiply by time. So I need to multiply the power. And so the power is this. If I'm running full load, I will get this. If I'm running at reduced speed, that would be this. I need to multiply this power time. How many hours does this persist? And so in this map, in this fictitious map, he said stay from 15 to 20 this much, and between 20 and 25 this much. You add those two guys together, basically pretty much stay full load all the time. And those are the total hour. So the megawatt hour is this time 8 turn. You multiply those three together, you get the megawatt hour. It was as simple as this. Questions? So unfortunately, this is also need to write what's given and what's required. And then you write the equation, which is basically the power is, the energy is the power multiplied by the time the number of the turbine. And you get the number right, you get the other 4 points. So that should have been an easy exam, right? Questions?